All right, welcome everyone to this third video here on chemical thermodynamics. So in this video, we're going to be talking about Gibbs free energy. Okay. So in the previous video, second video, right, we talked about how, again, the second law of thermodynamics tells us that if the entropy change of the universe is greater than zero, that process, that reaction, that thing is going to be a spontaneous change. Okay. Right. But again, we want to focus in on our chemical reaction and don't really care about measuring the entire universe. Right? We want to just care about our system, right? So what can we measure to tell us whether or not something is spontaneous just for the system? And that's where the Gibbs free energy comes in, okay? It is defined, right? It's the change in Gibbs free energy. So G here is this Gibbs free energy, right? So the change in Gibbs free energy is defined as the change in enthalpy minus temperature times the change in entropy, okay? This entire thing is just for the system, okay? This is all in the system, okay? And again, G is called the Gibbs free energy, and this tells us, okay, that when delta G is less than zero, your chemical reaction, your change will be spontaneous, okay? At some constant temperature pressure conditions, right? Conveniently for us, right, when we do chemical reactions in the lab, we're under constant temperature pressure conditions, right? So in chemistry, when we're focusing on our chemical reactions and things of that nature, right, that we can just look at this free energy change, okay, this Gibbs free energy change to measure whether or not something is spontaneous, and it's purely a system quantity, okay, where you're measuring the enthalpy change in the system, and the entropy change in the system in order to calculate the Gibbs free energy, okay. Now note here that, right, the second law of thermodynamics says delta S is greater than zero for the, right, delta S of the universe is greater than zero for a spontaneous process. Here, we're saying a process is spontaneous if delta G is less than zero, okay? Right? And so, right, that delta G being less than zero is equivalent to saying delta S of the universe is greater than zero, okay? And then this free energy change is also related with how much useful work you can get out, okay? So if you calculate this free energy change for an electrochemical reaction, which we'll talk about electrochemistry after thermodynamics, okay, you can use that to determine how much energy, how much voltage, how much power you can get out of, say, like a battery, okay, which a battery is just a giant electrochemical reaction, okay. So if I want to predict spontaneity, right, in a chemical reaction, I want to calculate its free energy change, delta G equaling delta H minus T delta S, okay. Now, right, if something is spontaneous, that means delta G is less than zero, okay? So the cases this occurs at, for example, is if delta H is less than zero and delta S is greater than zero, right? Again, we're subtracting delta S. So keep in mind, right, since we subtract delta S, okay, delta S being greater than zero and delta H being less than zero means delta G is always less than zero, right? Always, okay? Right, similarly, if delta S is less than zero and delta H is greater than zero, delta G is always greater than zero, right? It's never going to be less than zero, okay? And then we have the other two cases where if delta H is less than zero and delta S is less than zero, then this only has delta G less than zero at low temperatures, meaning the reaction is only spontaneous at low temperatures, right? While delta S being greater than zero and delta H being greater than zero means this reaction is only spontaneous at high temperatures, okay? Right, and what this is telling you, again, is the fact that a reaction to be spontaneous, it would love to be exothermic, right? It would love its enthalpy to decrease, and it would love entropy to increase, okay? So even for looking at just system-dependent quantities, right, things to be spontaneous, things want to go to higher entropies. Entropy wants to decrease, and your energy wants to decrease, right? So let me say that again, right? For a chemical reaction, your entropy wants to increase, and your enthalpy, your energy, wants to decrease for the reaction to be spontaneous, okay? Now, it doesn't mean that those two things have to be in that way for it to be spontaneous, right? You can have a decrease in entropy and a decrease in enthalpy and still have a spontaneous reaction that's just only spontaneous at low temperatures, okay? Right. And so yeah, right. So it just kind of depends on your chemical reaction, right, and whether or not the enthalpy increases or decreases, entropy increases or decreases. So kind of what temperature range your reaction is going to be spontaneous. Okay. Now note when you're calculating delta G, okay, often delta G and delta H itself are given in kilojoules, while delta S is given in joules per Kelvin. Okay, which means you need to multiply typically this quantity here by 1,000, okay, so that you can convert it to kilojoules. Okay, it's a very common mistake to forget to do that. So I wanted to point it out, right? Hammer this point home, right? That whenever you're calculating delta G, you typically want to make sure delta S is in kilojoules, and often it's given in joules. So to convert it to kilojoules, you just got to not multiply. Woo, that's a big mistake, right? We got to divide by 1,000, not multiply, right? We got to divide this guy by 1,000 in order to convert that to kilojoules. Not multiply, divide. Okay. All right. And then we're going to talk about entropy and Gibbs free energy changes for chemical reactions. But to do that, we need to define something called standard states. Okay. So the standard state of a substance is defined by the following set of rules. Okay. A pure element in its physical form that is thermodynamically most stable at 1 atmosphere, 25 degrees Celsius. Okay. If it's a gaseous compound, it's 1 atmosphere's pressure. If it's solid or liquid, it is pure, right? It's not a mixture, it's not a solution, right? It's just pure liquid or pure solid. And if you have an ion in a solution, then that ion's concentration is 1 molar. Okay. These define the standard states of an element. Okay. Right. And so often in chemical reactions, we concern ourselves with the changes in chemical reactions under standard conditions, okay? Because the enthalpy change, entropy change, and Gibbs free energy change of a reaction can depend on temperature, can depend on concentrations, and other things like that. So to be consistent when we're talking about these changes, right, to other people, reporting them in publications, right, in textbooks, reporting them online, things like that, right? We want to be consistent. So we'll often define things in terms of standard states. So this little superscript 0 here is indicating you're in your standard states, okay? Meaning pressures of 1 atmosphere, concentrations of 1 molar, things like that, okay? And so the enthalpy change for a reaction is related to the enthalpy of formation of the products minus the enthalpy of formation of the reactants times their stoichiometric coefficients, okay? Right? Right, that symbol here, right, is the sum symbol, or summing up all the reactants, all the products, okay? N and M are moles. Often these are coefficients, right, in our balanced chemical reaction, okay, our stoichiometric coefficients, okay, and then again, delta H, F here is your enthalpy of formation, something that's going to be given to you, right, you have to look it up in a table or something like that, okay, not something you'd ever remember or know, right. Similarly, to calculate entropy change for a reaction, same type of thing, okay, the entropy change for a reaction here, right, is related with the entropy of the products in their standard states minus the entropy change of the reactants in their standard states times their stoichiometric coefficients, okay, right. Now, entropy here is not an entropy of formation, it's just standard entropy, okay, and again, this is something that you obtain from the table, right, your book or something like that, okay, but the form of calculating this is the same as enthalpy, okay. And then for delta G, right, we can again use some sort of table and calculate the free energy change of a reaction, right, related to the free energy change of the formations of the products minus that the reactants times their stoichiometric coefficients, right? And this equivalence to kind of Hess's law and things like that that I talked about with enthalpy, right, and applied the same thing with entropy, okay? Or we can just use the equation delta G equals delta H minus T delta S, right? If we have delta H of the reaction, right, and delta S of the reaction, we can get delta G of the reaction, right, given the temperature, okay? right? And then finally, noting, right, that entropy and Gibbs free energy changes for reactions follow the same rules as enthalpy, right? That if you multiply a chemical reaction by a coefficient, you multiply those things by that same number, right? If you change the direction of a reaction, right, reverse the reaction, you change the sign of your enthalpy, entropy, or Gibbs free energy. Right? And if you add two reactions together, you add together the enthalpy, entropy, or Gibbs free energy of those reactions. Okay? So all three of those thermodynamic quantities, delta H, delta S, and delta G, all obey the same set of rules. Okay?